Okay, so in the intro video, we looked at Zeno's paradox, which led us to consider a certain infinite sum where we added up all the terms of a sequence. And I noted there that that's really what a series is. Okay, so I say here that a series is the sum of all the terms of some sequence. Okay, so in this video, we aim to make this a little bit more precise. Okay, what exactly does it mean to add up an infinite number of numbers? Okay, well, to do this, we're going to first start with a sequence a sub n. So in the case of Zeno's paradox, a sub n is 1 over 2 to the n. And then we'll go ahead and form what we'll call the sequence of partial sums. And I'll denote this by s sub n. So s1 here is a1, s2 is a1 plus a2, s3 is a1 plus a2 plus a3, so on and so forth. So s sub n is the sum of the first n terms of this sequence a sub n. So it's a1 plus a2 plus a3, and we keep adding until we get to the nth term of the sequence a sub n. Okay, now for Zeno, s1 is a half, s2 is a half plus a quarter, s3 is a half plus a quarter plus an eighth, so on and so forth. And in the last video, we just noted that s sub n is really just telling us the total distance traveled by Achilles on the nth stage of his trip. Okay, now for a sum of this form, we can write it in a more compact form using sigma notation, which you would have seen in Calc 1 and Calc 2 when working with integrals and Riemann sums. Okay, so I'm going to write this sum right here underlined in blue as follows. Okay, we're going to write this as the sum, that's what this capital Greek letter sigma is telling us to do, of a sub k, where we're going to let the index k range from 1 up to n. Okay, so the way this notation works, right, is I'm going to first plug in 1 for k, so that's going to give me a1, and then I add to that what I get when I plug in k equals 2, so plus a2. Then I add to that what I get when I plug in k is 3, so plus a3, so on and so forth until I get up to a sub n. All right, so now for Zeno, I'm just replacing a sub k with 1 over 2 to the k. All right, now for the series, right, we want to add up all of the terms of this sequence a sub n, and s sub n is really just the sum of the first n terms. So the idea now is to take the limit as we let the number of terms approach infinity. Okay, so we'll say that the limit of the sequence of partial sums is called an infinite series. And so by taking the limit of s sub n here as we let n approach infinity, well, first off, just note that this expression in the middle, I've just replaced s sub n with this expression here for s sub n in terms of sigma notation. And also note that as we let n approach infinity, and n is the upper bound here for our sum, okay, we can write that then notationally in a more compact form by just writing the sum as we let the index k go from 1 to infinity of a sub k. All right, and that is simply a1 plus a2 plus a3, and here we're going to continue to add, and what this expression really is telling us to do, right, is it's telling us to take this corresponding limit here of these partial sums. All right, cool. So with Zeno, again, I'm just replacing a sub k with 1 over 2 to the k, and as we noted in the last video, okay, S1's a half, S2 is 3/4, S3 is 7/8, so on and so forth, right? And S sub n, we argued using this figure right here, is equal to 1 minus 1 over 2 to the n. Remember, on the nth stage of Achilles' trip, okay, he is going to be 1 over 2 to the n units shy of the door, right, which is at 1. And so the total distance he's traveled on the nth stage would be 1 minus 1 over 2 to the n. And now, as we let n approach infinity, s sub n converges to 1, which of course is just the total distance from where he starts to the door. So this series here has a finite sum, and that sum is equal to 1. Okay, great. So Achilles reaches the door. Okay, so now let's go ahead and look at just a bit of terminology. So first, what is a convergent series? Okay, we've talked about convergent sequences. What's a convergent series? Well, if the limit of partial sums exists, then we're going to say that this corresponding series converges. Okay, so here again is just the example from Zeno's paradox. It's really the only example we've seen so far. And here, since the limit of these partial sums exists, right, then this corresponding series converges. Okay, and I'm going to write this little C with this arrow there as just a shorthand notation to say that this series is convergent. And in this particular case, the sum is 1. All right, so what if the limit of partial sums does not exist? Okay, in that case, we'll say that this corresponding series diverges. And as a simple example of a divergent series, let's take the sequence a sub k that is just equal to 1 for each term. Okay, so for S1, that would just be 1. S2 would be 1 plus 1, which is 2. S3 would be 1 plus 1 plus 1, that's 3. So on and so forth. So S sub n is just 1 added to itself n times, and that's just equal to n. And see, now if I take the limit of these partial sums, right, n will approach infinity. So here, the limit of the partial sums, S sub n, does not exist, right? The partial sums are not approaching any one specific value. And so we say that this corresponding series is divergent, right? Or put a little more informally, we're just saying that if I add 1 to itself an infinite number of times, then the sum will be infinite. All right, great. Well, that's a good place to stop. In the next video, we will just look at some more examples. Thanks so much.